Thank you very much for inviting me to talk today. So I'll tell you about some new developments in our understanding of non-perturbative topological string theory by making use of resurgence and a novel connection to notions from number theory and quantum modular forms. So this talk is based on a paper of mine from December 2022 and two recent follow-up papers with my collaborator Veronica from April this year. So let me start right away with some background. So performing a perturbative computation in a quantum theory means applying an approximation scheme and some small parameter, typically a coupling constant. So we're given, as a result, some formal power series that most often has a zero radius of convergence. And this divergence of perturbative series means that we cannot determine the original function uniquely because of the presence of some exponentially small non-analytic terms that are hidden in perturbation theory. Now, this is in particular the case of topological string theory. So if you take a Calabi-Yau threefold X and the free energy of the A-model topological string compactified on X, this is only defined perturbatively by a worldsheet genus expansion, as I write here, in the topological string coupling constant GS. And here the index G of the series is the worldsheet genus, and the functional coefficients Fg of T are the so-called fixed genus free energies. These are functions of the vector T of the Kähler parameters of the Calabi-Yau, and they're known to be well-defined convergent functions only in a common region near the large radius limit in moduli space. Now, if we fix the vector of Kähler parameters in that common region of convergence, then we have this numerical series, the Fg of T, and it is a relatively old result that this series diverges factorially, like 2g factorial as g goes to infinity. And this is signaling the presence of some non-analytic term in the topological string coupling constant that we would like to understand. Now, more generally, the divergence of perturbation theory in quantum theories, if some favorable circumstances applies, can be dealt with using the theory of resurgence. And when this is the case, it means that we can write observables unambiguously as Bures-sur-Yvette plus resum trans series. So we can get rid of the non-perturbative ambiguity by applying resurgence techniques. And what resurgence does when you're handed a generic asymptotic series is that it allows you to discover a structure of exponentially small corrections that characterize the non-perturbative sectors associated with your perturbative expansion, and it pairs them with a set of complex numbers known as Stokes constants, and these are particularly interesting for the rest of this talk. These Stokes constants are already hinted at the level of the perturbative series because they encode information about the large order behavior of the perturbative coefficients, but at the same time, they also characterize the non-perturbative sectors. Now, in some very remarkable cases, these complex numbers end up being actually integer or rational numbers, and they're conjecturally related to a numerative invariance of the underlying theory, often connected to BPS counting. And so I list here some examples where this applies. There's Super Young-Mills theory, complex Chern-Simons theory. But more interestingly for us today, topological string theory on Calabi-Yau threefolds and all various ways of approaching this. And there's this long list of results that go in this direction. And so this growing evidence that indeed we can use the theory of resurgence to systematically understand the non-perturbative sectors of topological string theory. And so before entering into the details of the story, I'll just give a very quick a recap of resurgence in general terms. This is just literally 2 slides where you can forget about topological strings for a moment and just take phi of z to be any simple resurgent Givre-1 asymptotic series. So the asymptotic coefficients have a large order growth of the form exponential times factorial. Now, when we are given this asymptotic series, what we usually do is the first step is we take the Borel transform, which means we just factor out the factorial divergence of the coefficients. And the result is this germ of an analytic function phi at of zeta, which is now analytic at the origin. But it generally has a pattern of singularities in the complex zeta plane. And I denote this by zeta omega. Now, if I fix an angle theta in the Borel plane that doesn't pass through any of the singular points, then I can take the Laplace transform of the Borel transform, and that gives me the Borel-Laplace resummation of the original asymptotic series. That is now a locally analytic function in the original variable z, but it has, in some sense, inherited the singular structure of the Borel transform, because now we have discontinuous jumps across all rays in the complex z plane that correspond to the arguments of the singular points of the Borel transform. Now, I told you that we're interested in the simple case, so only simple poles or logarithmic branch points, because it's a physically relevant case. So let's take zeta omega to be a logarithmic branch point. We can always consider the local expansion of the Borel transform at the singularity, zeta omega. And what we observe if we remove the regular part that's encoded in the dots is, of course, the logarithmic singular behavior, but also a perturbative locally analytic series attached to it. So this phi hat omega is locally analytic at the singular point zeta omega. And I use this notation with the hat to signal the fact that we think about it as the Borel transform of some asymptotic series. And I also factor out this complex number as omega, that is the Stokes constant. And where whenever a line in the complex plane passes through a singular point of the Borel transform, we call that a Stokes ray. Yeah, so here I am assuming that zeta omega is a logarithmic branch point, and then this is what I expect the local behavior to be. In general, in all of my examples, we see this type of singular points or simple poles. So we don't see more complicated power laws, but from the point of view of resurgence, you can, of course, study those cases as well.
Right. Let me see the Stokes constant here to hold the large order behavior of the original phi. I think you made a comment about this.
Yes. So actually, I won't really tell you that bit of information, but because I will not use it explicitly. But basically, if you study the you can write some large order relations that are satisfied by the perturbative coefficients of the asymptotic series. And in some sense, they are a generalization of this very simple, large order behavior. And then you can see that basically the leading order term in the large order behavior of the perturbative coefficients is given by the strongest singularity. That's the one that's closest to the origin. And so what contributes is exactly the perturbative series here and the S omega. And you can also include all the subsequent singularities, and so you get all of them. Okay, so let's say we fix the Stokes ray. There's two operations that we can perform. So if we take two rays that are slightly below and slightly above the Stokes ray rho theta, and we compute the lateral Bures-Laplace resummations along these rays, then we can take the average of these resummations, and that's by definition the median resummation of the asymptotic series, or we can take the difference, and that's by definition it's discontinuity across the Stokes ray. Now, in the case of the discontinuity, we can deform the contour. So by the standard contour deformation argument, we can see that actually this difference of resummations is just a difference of two integrals, can be written as an infinite sum of contributions, one from each singular points along the Stokes ray. And the contributions are again given by the same ingredients that we already saw appearing in the local behavior of the Borel transform, that are the Stokes constant, this phi omega that is the inverse Borel transform of the phi omega hat that I showed a minute ago, and then the location of the singularity zeta omega that's dictating the strength of the exponentially small correction, the non-analytic term e to the minus zeta omega over z. Now, this is schematically the process I've described has brought us from a single asymptotic series phi to a whole collection of new asymptotic series phi omega, and attached to them this collection of complex numbers, the Stokes constants. Now we can repeat this procedure with each asymptotic series that we've built this way and find new Stokes constant, new asymptotic series. Now to introduce a bit of order that's going to allow us to deal with these objects more efficiently, I want to remind you quickly of the notion of basic trans-series. That means we take each asymptotic series and we promote it to a non-perturbative object simply by multiplying it by the corresponding exponentially small factor. And so we introduce this capital phi of omega. Now, if we think in terms of basic trans-series, then the lateral Bures-Laplace summations, this s theta plus and s theta minus, can be interpreted as operators. And then we can define the Stokes automorphism across a given Stokes ray by this composition of operators here. And now the very last two pieces of notation. So if we collect all the basic trans-series that are closed under the action of the Stokes automorphism, and we get the smallest subset that is closed under the action of the Stokes automorphism, then we call this the minimal resurgent structure of the original asymptotic series. So we have, in some sense, we have identified this subset omega bar of the whole collection of singular points. And correspondingly, we can define a matrix of Stokes constants with this curly S of phi. Okay, so this is all I wanted to recall in terms of resurgence. So let me move on to the object I want to apply resurgence to. That is this in the context of topological string theories and Calabi-Yau geometries. So now let X be a toric Calabi-Yau threefold. We know by local mirror symmetry that this is always associated with an algebraic curve sigma in C star times C star. I denote by G sigma its genus. And we know that this in some appropriate way describes the B model topological string on the mirror Calabi-Yau X tilde. Now, once we have this mirror curve sigma, we can apply Weyl quantization to it, and we obtain a collection of quantum mechanical operators, this rho J, where J goes from 1 to the genus, acting on L2R, so they're really quantum mechanical operators, and they have very nice properties as soon as we assume some mild hypothesis on the mass parameters of the Calabi-Yau, that is, they're positive definite and they're trace class. So because we know they possess these properties, well, it's conjectured in general, but we verify it in examples, we can compute the generalized Fredholm determinant of the entire collection of operators. This is parameterized by the mass parameters again. It depends on the Planck constant that's introduced by the quantization procedure. But most importantly, it's an entire function in the moduli space of complex deformation parameters J of the mirror of the Calabi-Yau. So one thing we can do is take the local expansion at the origin. So this is a well-defined local expansion. And in particular, the functional coefficients will be analytic functions of the Planck constant h bar. Now, of course, you don't depend anymore on the complex deformation parameters as we're expanding at kappa equals 0, but they have this dependence on the vector of integers capital N. Now, these functions here are the so-called fermionic spectral traces and are the objects I'll mostly be interested in, and I hope it will be clear why in a second. But importantly, because we want to apply resurgence to them, let me also mention that I assume I can always analytically continue them to the complex plane minus the negative reals. But then I verify this in all examples where I actually perform some explicit computations. And so why are these Zs important, and how are they actually related to the free energies of the topological strings? This is a statement of the topological string spectral theory correspondence that's been proposed not so long ago. And it can be made very precise, and it takes the form of this integral transform. Basically, the fermionic spectral traces are given by this integral over the exponential of a function j, which is called the total ground potential of the A-model topological string. And this is a function that is entirely well-defined from the side of the topological string alone. Here, I'm just introducing the variables mu j's that are the logarithms of the complex deformation parameters. But the important thing is that this function j, this total ground potential, encodes the contribution of two terms. We have a worldsheet ground potential that contains the standard free energy of the topological string. That's the one I showed in the very first slide. But it also contains a WKB term that is given by the Nekrasov-Shatashvili topological string free energies. And you know a bit about the refined version of the topological string, then you might know that this can be regarded as non-perturbative corrections of one another in the suitable regimes. And I'm mentioning this because in some sense it will come back in the picture I'll try to describe. So one last piece of background is that the TSST correspondence comes equipped with a strong weak coupling duality, and precisely the coupling constant of the string GS is the inverse of the Planck constant h bar. And maybe I'll close this section mentioning that, so because of this statement of the TSST correspondence, the fermionic spectral traces gives us access to the non-perturbative sector of topological string theory, and in particular to these non-perturbative effects that are signaled by the divergence of the perturbative series in some way, in the same way that you might think of large n-gauge string dualities. But at the same time, it doesn't allow us to systematically understand these non-perturbative effects, and that's why we apply resurgence to them. So
the thing that is absent when you consider compact?
Sorry, what?
You said it's a math parameter. What's
yes. So basically, when going to the B model, so if you apply local mirror symmetry, you go to the B model topological string. This mirror Calabi-Yau will have a collection of complex deformation parameters, but there's only there's a number of them that is equal to the genus of the mirror curve, that in some sense you can geometrically understand as true complex parameters of the moduli space, and the rest, yeah, you can think of them as mass parameters, as they don't really matter geometrically. Yeah. And yes, and indeed they're not important. In the main example I'll describe, there's no mass parameters. And okay, so let me enter into the details finally. So what is the resurgent structure of these fermionic spectral traces? So we fix the vector n of integers, and we take the logarithms of the fermionic spectral traces. Then we get two dual asymptotic expansions if we consider either the weak or the strong coupling limits in h bar. And these are expected to be Gevrey-1 and simple resurgent, and so we can ask ourselves, what is the minimal resurgent structure? So first in the paper by Jigu, Marcus Marini in 2021, and then in my paper, we study some examples, and then we conjecture in general this picture. So let me just take the limit h bar going to 0 first, then the dual limit will be somewhat analogous. So what we observe is this peacock pattern of singularities in the Borel plane. It means that, so if you look at the Borel transform, the singular points are all located along vertical towers, and there's finitely many of them. And these are indexed by the sigma here that goes from 0 to L0. But if you look at each individual tower, then there's infinitely many singular points. And importantly, the distance between consecutive points is always the same, and it's given by this constant A0 here. Moreover, if you think about the basic term series, then you can see that the perturbative term attached to the exponential correction is only indexed by the label of the tower sigma. So it's the same for every point along the same tower, while the index n that distinguishes the different points on a single tower enters the exponential. At the same time, we also observe something that is equally important, that is all the Stokes constants, if we normalize the perturbative series appropriately, are actually rational numbers. And so we conjecture that they should be somehow related with enumerative invariance of the geometry. Now, this picture is observed and conjectured entirely analogously in the opposite regime, where h bar goes to infinity. And that corresponds, if you remember the duality, to the weakly interacting regime of the topological string. And now I only want to point out the difference in notation because I'll use it again. So I just use the letter psi to denote the perturbative series. And of course, we have a different fundamental constant A infinity, and a priori a different number of vertical towers. But again, the Stokes constants are all integer numbers, and I denote them with the letter capital R, and we see, of course, these peacock patterns. Now, in both limits, it turns out in the examples that it is particularly helpful to construct the generating series of Stokes constants over the index small n. So this Q series will play a particularly important role in understanding the enumerative and number theoretic content of this collection of numbers. And so I want to point it out in general here already. Now, to conclude this general picture, let me recap. So we observe peacock patterns in the Borel plane and associated to these infinitely many rational Stokes constants. And we conjecture that these are somehow related to enumerative invariance of the geometry. As a last comment, these peacock patterns are not only observed in topological strings in the spectral theory dual to topological strings, but they're also observed in other theories. But they have in common the fact that they all seem to be controlled by some quantized algebraic curve. And for example, there's complex Chern-Simons theory in these examples. Okay, now the rest of this talk, more or less, I will focus on the example of local P2. Well, first I'll focus on the example of local P2, and then I'll try to give you a generalization of the picture I'm gonna describe. Local P2 is the benchmark examples of toric Calabi-Yau threefolds, so that's why we started with this particular case, and it turned out to be more interesting than we had expected in some sense. So the local P2 Calabi-Yau is the total space of the canonical line bundle of the projective surface. So this has no mass parameters, but it has one complex modulus. So the mirror curve is only genus 1. Now, in this particular case, the spectral trace of the operator that comes from quantizing the mirror curve, it is known in closed form in this factorized where we have, these are the Q Pokammer symbols that Campbell has introduced before. So we have Q and Q tilde series that are written in terms of this variable b squared, as you probably have seen in other contexts before. And b squared is simply proportional to h bar. Well, w is just a constant. Now, starting with this anti-holomorphic factorization of the spectral trace, we can perturbatively expand it at all orders in h bar, both at weak and strong coupling. So I use the letter tau defined in this way because it's a bit simpler to think about both series as small parameter expansions. So the strong coupling will be tau going to 0. And we get this series phi of h bar and psi of tau that are Gievre 1 asymptotic series, and the coefficients are known in closed form. And they have the expected factorial divergence. Now, what is important is because we have this closed form for the coefficients, then we can compute exactly the resurgent structures, weak and strong coupling. And so in particular, we can compute the Borel transform and analytically resume them as exact functions of zeta, these are not just simple resurgent functions, but they have the Borel planes are very simple. There is one tower of logarithmic branch points along the imaginary axis for each of them. Here the purple is weak coupling and the blue is strong coupling. And if you look at the secondary resurgent series at each of the points along this tower, then they're all trivial. They're all they can be all normalized to 1. And so in some sense, in this example, all the non-perturbative content of the resurgent structure is contained in the Stokes constant. And if we normalize the Stokes constants, then we can see that actually you can prove that these are given in closed form by divisor sum functions. And I write here the explicit expressions. So we have this sum over the positive divisors d of n of 1 over d times this is the Dirichlet character modulo 3 that associates to d is fundamental congruence cross, so 0, 1 or minus 1 modulo 3. And then at strong coupling, we have the same expression, but the divisor d here in front of the character is exchanged with the arithmetically dual divisor n over d. And note that these are not just rational numbers, but if you multiply each of them by n, then you actually compute a sequence of integer numbers. And these are the integer numbers I'm mostly interested in, and they're conjecturally related to enumerative invariance of the geometry. Now, this very simple arithmetic duality between the two collections of Stokes constants can be upgraded into a much richer structure. So there is two sides in this constructions. So let me try to describe both of them individually and then try to put them together. So once you're given this sequences of numbers, the Sn and the Rn, then there's two things you can do. One is you construct the Dirichlet series of the Stokes constants, and the other is you might think about their generating function, the generating series, actually. So if you take the Dirichlet series of the Stokes constants, then we prove that these are analytically continued to weak and strong coupling L functions. So this is highly non-trivial, the fact that just by constructing this Dirichlet series, we get L functions out of them. But on top of these are not just any L functions, then you can write them in factorized expressions. And you see that the factors, apart from the normalization, are the same. So you have the Dirichlet L function associated with the character and the Riemann zeta function. And these two L functions are given by each other up to normalization once you exchange the arguments in the factors. And so there is this communication between the weak and strong coupling regimes that kind of hints at the global strong-weak symmetry that I will describe in the next slide. But first, let me tell you the other side of the story. That is, if you take the generating series of the Stokes constants instead of the Dirichlet series, now this equals the discontinuity, if you want, almost by construction, because of how this tower is displayed. But the important thing is you can resum it into these closed forms that are exactly the Q tilde and Q blocks, so that appear in the factorized expression for the spectral trace. So the point here is that if you take the Q block and you expand it perturbatively at weak coupling, then you get the perturbative expansion. But somehow you recover it as giving the non-perturbative contribution at strong coupling. And this is true also for the other block. So there's this exchange of perturbative and non-perturbative contributions between the two regimes. This is an exact statement, it's not just an intuitive connection. And so these two theorems, together with some other corollaries, can be put together, connecting the resurgent structures at weak and strong coupling into a commutative diagram, which we use to describe what we call the strong-weak resurgent symmetry. So if the phi of h bar, you remember, is the weak coupling perturbative expansion, and the psi of tau is the strong coupling perturbative expansion. And if you follow the directed arrows in this diagram, which are all proven exact statements, you can recover all the vertices. And in particular, you connect exactly the weak with the strong regimes. And just taking a step back and thinking in more physical terms again, we can interpret intuitively this strong-weak resurgent symmetry as coming from the S-type duality that exchanges the worldsheet and the WKB contributions to that function J that I showed and I called the total ground potential of the topological string. And so this is a very unexpected analytic number theoretic symmetry that comes from studying the resurgence of this series. But there is one additional ingredient that I haven't showed yet, one last arrow in this diagram that comes from just thinking about the weak and strong coupling L functions. So if you know something about L functions, then you probably ask yourself, how are these two L functions analytically continued to the rest of the complex plane? So the completions of the weak and strong coupling L functions that we denote with the letter lambda, 0 and infinity, you might expect them to satisfy a standard functional equation of the form I write here for the Riemann zeta function. But turns out that this is not true. They do not individually satisfy this functional equation. What they satisfy is instead a combined functional equation. So lambda 0 of s is equal to lambda infinity of minus s. So to meromorphically complete the weak coupling L function, you need the strong coupling one and vice versa. And now it is exactly this complicated picture here that in our last paper we tried to generalize to a theory of modular resurgence that now in principle has nothing to do with topological strings anymore. And so in the rest of the talk, I'm just gonna quickly describe this theory. So the first step is identifying a new class of asymptotic series that in some sense reproduce the main ingredients of the local P2 case. And we do this by introducing the notion of modular resurgent structure. So this is a definition that we propose. So we take a Gevrey-1 asymptotic series phi of y, and we say that it has a modular resurgent structure if it satisfies two conditions. One is that the Borel transform has this tower of singular points in the Borel plane, and the resurgent series at each singular point is just given by the Stokes constant. And the other is that the Stokes constant, once you package them together into Dirichlet series, they actually give two L functions. Now here we have two, well, before I only described one for each limit, just because in principle, we admit the case where this A m's and A minus m's might not be symmetric. In the local P2 case, there is a clear symmetry once you change m into minus m for the Stokes constant. So we just consider 1/2 of the collection. So by L function, I mean that, so this Dirichlet series must have this Euler product expansion over the prime numbers, and it must be convergent in some right half plane of the complex numbers. Yeah, so I think that's a point we're still kind of trying to understand precisely. So what is the actual role played by the functional equation in the general picture? And we want to characterize that better, but we haven't done so. So that's why there's no, like, the functional equation doesn't enter the definition yet. And so is a side comment here. I don't talk about generating series, only about the L functions, but we can equivalently characterize this modular resurgent series in terms of the generating function f of y, that again has this definition in the two half planes of the complex plane. And you can just go from one to the other by using the canonical correspondence between L functions and Q series that goes by Mellin transform and inverse Mellin transform. So you can think about this in two different ways. But so what is the general paradigm that we propose? First, let me just give you a hint. If you take this generating function f of y and you expand it as y goes to 0 in both upper and lower half planes, then you get some asymptotic series f tilde plus minus of y. And you can write, so you can prove this, you can write this perturbative coefficients in terms of the corresponding L function evaluated at minus n. So this means that the asymptotic expansion of the generating function is encoded in the analytic continuation of the L function. So this type of number theoretic statement is just a hint at a richer structure that we try to describe in this new paradigm of modular resurgence, and in general underlies the properties of all this modular resurgence series. So because I don't have time to enter into the details of all the statements, I'm again going to give you just a commutative diagram to be able to look at the big picture in one. And so what we observe is that there is again a network of exact relations that connects pairs of modular resurgent structures. In terms of generating functions, we have this f0 of y and f infinity of y. Now we use the f0 f infinity notation because this is a generalization of the strong weak resurgent symmetry of local P2. In some sense, it is a generalization. In another sense, is a simplification. But there is no underlying meaning of strong weak coupling in this context. It's just a pair of modular resurgent structures that are connected in this way. And in particular, there is a functional equation that connects the two corresponding, L functions. Now, so this is what we call the paradigm of modular resurgence, and there is one very last ingredient in this picture that's been missing so far, but I mentioned at the beginning, that's quantum modular forms. So basically, we conjecture deep relation between these modular resurgent structures and quantum modular forms. Before telling you the conjecture, let me just quickly recall the definition of Zagier. This probably looks more familiar after the introduction by Campbell on quantum modular forms, even if in this case these are not vector valued. So I take a function f from h to c, so valued in the complex numbers, a subgroup gamma in SL2Z, and omega is either an integer or an alpha integer. That's the weight of the holomorphic quantum modular form. So this function has to satisfy this property to be called as such. The co-cycle, that's this difference here, has to be holomorphic in the cat plane corresponding to the element gamma in the subgroup here. So for every choice of gamma in the subgroup capital gamma, then you can build this co-cycle as the difference of these two terms, and it has to be holomorphic in the corresponding cat plane. So for a classic modular form, this difference would be 0. And so the conjecture is that if you take f to be a Q series defined in the upper half plane with values in C, and we write Q as e to the 2 pi iy, then we asymptotically expand it for y going to 0 in the upper half plane. If this is a modular resurgent structure, then f of y is a holomorphic quantum modular form for some subgroup of SL2Z, and we can reconstruct it by taking the Millian resummation of the corresponding asymptotic expansion. So we have again this this connection between modular resurgent structures and quantum modular forms, and this statement on the resummation. Now this is proven for the generating functions of the Stokes for local P2. That's where we started. In that case, the subgroup is the congruent subgroup gamma 1, 3. This is also deeply related to the geometry of the problem. But we also have other examples. We constructed a class of examples from mass-cas forms, and there's evidence a bit sparse in the literature on combinatorics and the quantum invariance of knots in tree manifolds. Okay, and this is more or less everything I wanted to say, except I will just give you some very brief conclusions. So first of all, the key takeaways in my talk, you can always construct the spectral traces of a given toric Calabi-Yau threefold. And then you can ask what resurgence of these spectral traces is. And it turns out that there is a universal structure of peacock patterns and rational Stokes constants that are conjecturally related to the enumerative invariance of the geometry. Now, if you look in particular at the case of local P2, and you study both regimes in H bar, or if you want, both regimes in GS, then the entirety of the two resurgent structures can be embedded into one commutative diagram that describes the so-called strong-weak resurgent symmetry, and can be intuitively traced back to physical dualities at the level of the topological string. And finally, these results on local P2 suggested this new paradigm linking the properties of Q series, L functions, and quantum modular forms via resurgence. And so we call this a modular resurgence paradigm, modular resurgence structures. There's a lot of open questions in this direction of research, and they're mostly work in progress. So I didn't enter into the details of what is the physical geometric interpretation of the Stokes constants. So what are these enumerative invariants actually? So this is still work in progress. then it would be very interesting to use the dictionary of the TSST correspondence more explicitly to connect to the topological string side of the correspondence and state this strong weak symmetry in more concrete terms at the level of the free energies, and compare it with other results, recent results in the literature that study the resurgence of the free energies directly via the holomorphic anomaly equations, and there's many papers by Marcos Marinho on this, and have more examples. So more examples from topological string theory, but also in general, more examples in the modular resurgence category. And lastly, also, there was a question on this, actually try to fully characterize whether these admissible L functions and their functional equation, and try to maybe use this in proving the conjectures related to modular resurgence. And that is all. Thank you.
Maybe this pertains to your third point in the open questions, but so in the case of local P2, there's also this nice sort of simplification of the story where it's only the Stokes constant and you don't have to worry about these series I had that you described. Do you know how those would fit in a big diagram that you're drawing?
Yeah, so there is an idea on how to proceed in that sense, because even though so the general case is still conjectured to be this peacock pattern, right, for all toric Calabi-Yau threefolds. And the peacock pattern still has a crucial simplification. That is, if you fix the tower, all the perturbative series are the same. So one idea would be to try to understand the generalization of this picture in that direction. So consider the collection of Stokes over each tower, and there's possibly a way to work around the fact that you have this perturbative series that multiplies all of them, right? So that's one thing that would be maybe one of the most immediate generalizations that we're working on. Yeah, I mean, yeah. I mean, it's even a bit broader of a picture, because like these peacock patterns can be found in other examples as well. So there is a chance that we might generalize this to peacock patterns.
We expect that there's a natural class of examples where you get classical modular forms as opposed to like cosine equation is 0, or this never happens.
I guess I guess not really. I mean, for the interesting examples, right? Because I mean, this holomorphic quantum modular forms, you can construct them starting from classic modular forms, but I mean, this modular resurgent structure here encoded in this diagram, I don't think we would be able to see this. Maybe Veronica can.
Because if you take the L function, for instance, of a classical modular form, then essentially after you write this FTP, you take the inverse, get something convergent.
You don't see this.
Yeah, there's no Stokes constant.
Yeah, like it's a bit too trivial to, yeah.
I mean,
it's trivial resurgence.
Oh, it was because what we did is like if you take the function of a modular form, and then if you take the actual modular form plus take the Fourier coefficient times some error function. With this modification, then you end up closing the cycle in this way.
But you are like
You have to force a little bit, so just the platform itself doesn't work, but if you add these function with the same three coefficient that we play the role of the cosine.
You're like forcing it to become quantum, right? You're adding the piece. So
you start with doing K-pi extension. So K-pi will give you complex moduli parameter.
yes.
How does it? So I'm used to to use like as a moduli parameter the one that enters in the P2 equation. So it becomes Z of psi most of the time.
Yeah, in the Picard-Fock equation.
Yeah. How does it work in this K-pi?
I think so. The Z usually the battery of coordinate is usually what is used in the Picard-Fock equation. Yeah. I think the relation is just that the Z is the K is 1 over Z cubed, something like that.
What kind of extension? Large measures? Is there a canonical point?
This is the orbifold. This is the orbifold. This kappa equals to 0. I mean, another interesting idea would be to, yeah, maybe because these are entire functions defined in the whole moduli space. So one could think about expansions around order points in moduli space, but the standard construction is this, so that's where we started from.
I thought the TSST was based on, so when you do the natural thing, it goes at all conical points.
So the thing is, if you take this expression here, so the J is naturally defined in the large radius because that's where the free energies, right? If you write down the free energies, those are usually well defined around the large radius point. And so here in the right-hand side, this J makes sense as an expansion at large radius. Now, if you take the limit where h bar goes to infinity, that's GS goes to 0, so the weak coupling of the string, then you can simplify this, and then you can also perform this integral. And what it turns out that you're left with the exponential of the free energies at the conifold point. But you have to perform this operation.
Okay, I propose we postpone the question to after the talk.